Hey everybody, and welcome back to my Hanson Math YouTube video channel. This is a pre-calculus video on finding limits analytically. Before we start, I will note that in the comment section below the video here on YouTube, you will find a link to a PDF file of the document that I am using to write on the screen with all of the examples and the y'all try problems. And I will also have the link to a PDF of the answer key. So with that in mind, here we go. In this section, we'll look at finding limits from an analytical perspective. We are going to explore limits of continuous functions. That is, these are not disconnected or piecewise in separate pieces using separate equations. So let's look at scenario one. Scenario one says if f of c equals a finite number, then we can conclude that the limit as x approaches c of f of x equals f of c. Well, what does that mean to you in English? That means that in this scenario, the function value and the limit value will be exactly the same. So there are no holes where you're looking at the limit. There's no discontinuities, no funny stuff. How do you tell? Well, when you plug in the values, such as on this first example here, when we plug in -3 for x, if you get a finite number, meaning that you don't get division by 0, nothing crazy like that, if you get a tangible number, so to speak, then that means that the function value and the limit value are the same. Okay, so let's take a look. Let's replace x here with -3. So we'll have -3 squared plus 5 times -3 plus 4. So now we'll crunch this out. -3 squared is 9. 5 times -3 is -15 plus 4. All this good stuff adds up to, let's see, 9 minus 15 plus 4. That should be -2. So the limit here as x approaches -3 is -2. This was done purely analytically by plugging in the limit value as x approaches -3. And since we get a firm answer at -2 and not anything undefined or division by 0, this is the deal. So even though this lesson is on an analytic approach, let's just take a peek at the graph in Desmos and see if we can confirm that as x approaches -3, you do approach a y value of -2. Okay, so here you can see our function. It's a parabola. And if we look at x approaching -3, if I trace here, you'll see right at -3, I am at -2, okay? And you can see here that we're clearly at a height of -2 on the y-axis, so that's the deal. So for this one, the limit and the function value are the same thing. In our next example, let's look at the limit as x approaches 4 for the function x plus 6 over x. Well, let's plug in that value of 4. So we have 4 plus 6 over x is worth 4, which would be 10 over 4. If we divide numerator and denominator by 2, we'll get 5 over 2, which is our limit. It also maybe could be helpful to look at that as 5/2. 5 divided by 2 is 2.5. So the limit is 5/2 or 2.5. Okay, that was simply done by plugging in. Let's take a quick peek at the graph to confirm. Here is our graph, and as we approach x as we approach 4, the limit of 4, you'll see that exactly at 4, we are at a height of 2.5, 2.5, which is consistent on both sides. So there you have it. As you approach 4, you have a limit and or a function value of 2.5. At this point, you should prepare to pause my YouTube video, and you should try on your own. Y'all try A and y'all try B using the techniques I've outlined in this scenario, showing all the work just as I've done. When you're all set with y'all try A and B, please feel free to resume the video, and we're about to move on to scenario 2. Okay, now we're moving forward onto scenario 2. This scenario states that if f of c equals a non-zero number divided by 0, then the limit as x approaches c of f of x is going to equal either negative infinity, infinity, or does not exist. So the crux of this situation here is that it will be does not exist, but there's also an instance where negative infinity or infinity is also an acceptable answer. But really the thing to think about is with this scenario where you have something divided by 0, it does not exist. All right. So to illustrate this, let's look at these two examples, starting with the first. The limit as x approaches 4 of the function 1 over x minus 4. So what I want you to do is I want you to substitute in 4 first. So you have 1 over 4 minus 4, which is 1 over 0, which gives us this scenario. We have any number, in this case 1 over 0. So what do you do here? Well, unfortunately, I don't know of any cool algebraic tricks to work on this, work my magic. So what I'd like to do is analytically look at a table of values, looking at values very near to 4, as that's the value we're approaching. So I'm going to look on both sides of 4. So I'm going to pick 3.9, and then get a little bit closer, 3.99, and then 4 exactly, which we know what's going to happen due to dividing by 0. I can already write in that's going to be undefined. Again, that's due to division by 0. And then a little bit past 4, so 4.01, and then a little bit larger, 4.1. Okay? Now, you can punch this into your TI 83 or 84 and go into the table, set the table to ask, and you can put these in, or you can do plug and chug. To save time here, I'm just going to put in the function values. When you plug 3.9 into this original equation, you get negative 10. When you plug in 3.99, you get negative 100. Plugging in 4 is undefined because the division by 0. 4.01, you get 100, and 4.1, you get 10. So here is the takeaway I want you to get out of this. If you look at these two x values lesser than 4, you get negative outputs for the y. And for the two x values I picked greater than 4, you get positive outputs for y. So it's a switch from negative to positive, which means that the graph is going to be going in two different directions, which we'll see in a second. So since it's going in two different directions, it's clearly just there is no limit. It does not exist. Okay? So I want to show you a little bit more what I mean about this negative and then positive piece on the graph. But this is one way you can see it in the table. You'll have a change of signs. You'll have negative on one side of the undefined, and it'll switch signs to positive on the other side. So now let's take a look at the graph and see how that manifests itself graphically. All right, so here is the value we're approaching here at 4. You can see that as we start tracing along the blue curve on the left side approaching 4, the function pitches down to negative infinity. And you can see that if we approach 4 from the right, getting closer and closer to 4, this branch heads upward, which is positive infinity. So again, it's a conflict. All right, you're not approaching a single or consistent limit value. The right side's going to infinity, the left side's going to negative infinity. So this is a case of does not exist, which also can be seen in the table as I've attempted to show you. I hope it makes some sense. All right, let's look at one more here in scenario 2. And we have now the limit as x approaches -1 of x over x plus 1 quantity squared. So what we'll do is we'll replace x with this -1. So we've got -1 over -1 plus 1 quantity squared, which would be -1 over 0. So again, we have division by 0. So we're going to be undefined at -1 in the domain, okay? But that still isn't really instructive of what the limit might be. So since we have a non-zero number divided by 0, let's look at the table of values very close to the number we want to approach. So I want to look at both sides of -1. So to the left of -1, I would have -1.1 and -1.01, and then -1 itself. And then to the right of -1, I'd have -0.99, and then moving further to the right, -0.9. Now, using the table on my calculator or plug and chug, you'll find out that when you plug in a -1.1, you get -110. You plug in a -1.01, you get -10,100. Of course, when you plugged in the -1, you were undefined because of division by 0. Plugging in the -0.99, you get -9,900. And plugging in the -0.9, you get -90. So if you look at the signs this time, what you'll see is the values to the left of -1 are both negative, and the values to the right of -1 are also both negative. So since they're consistent, you can say, since they're negative, that you're approaching negative infinity. The graph is going to be pitching down towards negative infinity. But you also could say that the limit does not exist, because infinity really isn't a limit, right? It goes on forever. But you may say negative infinity because that's the way the graph is trending. So either one of these is fine by me. And some textbooks will show one way, some will show the other. So this is the table approach to why the limit does not exist, or you could say it heads towards negative infinity. Now let's take a look at the graph and see how that bears this out. Well, here's our graph, and we can see as we approach -1, -1 is right here, okay? So as we approach that x value, from the left, our graph goes down forever. And from the right, as we try to approach x equals -1, it also goes down forever. So that's the idea of the limit being negative infinity, because it's consistently going down. Or you might want to say, well, Mr. Hansen, I think you're crazy, because infinity is not a limit. You'll never get there. You may also put does not exist. Either one is fine, just depending on how you think of it. I hope this makes some sense. Now that we've finished up with my examples for scenario 2, I want you to give it a try. So please hit pause and complete y'all try C and y'all try D. When you're done with both of those to the best of your ability, you may resume the video and we'll wrap this up with scenario 3. So go ahead and knock these out, hit pause, and when you're done, let's boot it right back up. Well, you've made it. It's time for scenario 3. Scenario 3 says if f of c, plugging in the limit value, results in 0 divided by 0, then we need to simplify or factor the function and then evaluate it all over again. All right? Well, let's see what it entails by simplifying or factoring. We'll look at 3 examples together and see how this works. But first, we'll do our traditional approach. You know, if you could plug in the limit value and get something finite, not undefined, then we'd be good. So we got to see what's going to happen here. So let's go ahead and plug in 0 for x, because that's the limit we want to approach. And let's take a look at what's going to happen here. So as I talk and do this, we'll see that we have 0 squared minus 3 times 0, well, that's going to be 0. 0 squared plus 5 times 0, that's going to be 0. So doggone it, there's our 0 over 0 scenario, which I'm calling scenario 3. So instead of doing a table on this one, we can do some algebra to simplify and then evaluate again. It's pretty cool how this one works. So you have to be a little bit of an inspector. So if you look at this one, you should notice that the numerator has x squared and 3x, and the denominator has x squared and 5x. They both contain x, so you can factor it out. So what you need to do is I want you to rewrite the limit as x approaches 0. You should rewrite this limit all the way until the final substitution. And now we're going to take this and we're going to factor out an x. So if you factor out the x from x squared, you're left with an x minus, if you factor out the x, you're just left with the 3. Over, factor out the x. If we pull it out from x squared, we're left with just an x. Plus, if we pulled out the x, we're left with just the 5. Now, look what happens here. This is pretty cool. These x's cancel out. So you're just left with the limit as x approaches 0 of x minus 3 over x plus 5. Now, when you plug in the 0 for the limit, you're not going to get division by 0 undefined. You're going to get a finite answer. So let's do that. Substituting in 0 for x, you have 0 minus 3 over 0 plus 5, excuse me. So that would just be -3/5, which would be your limit. If you change that into a decimal, 3/5 is 0.6, so it would be a -0.6. All right? So that is a tactic using simplifying or factoring to break it down and then evaluate it again. So let's take a quick peek on Desmos and see where this -0.6 is coming from. So now we're looking at the graph. If I put the mouse right at 0, you may or may not be able to see it says 0 comma undefined. So even though there's a hole at x equals 0, the limit as x approaches 0 is not the same, because you can see from the left and the right, you're approaching a consistent height on the y-axis, which if I go a little bit to the left, it says -0.603, and a little bit to the right, it's -0.597. Those values sandwich or converge on the -0.6. I don't know if you can see here that it's in fifths, 1, 2, 3, so it'd be at -3/5 right there. Moving on to the middle example, where we have the limit as x approaches 2 of x squared minus 4 over x minus 2. Let's start by plugging in this limit value of 2. So doing so, we would have 2 squared minus 4 over 2 minus 2. So we have 2 squared, which is 4 minus 4 is 0, and 2 minus 2 is 0. So we got the doggone 0 over 0 again. But since we have that, we are going to attempt to simplify. So what can we do about x squared minus 4? Well, if you're an astute algebra observer, you'll notice that that is the difference of squares. So I can rewrite the limit as x approaches 2, and instead of x squared minus 4, I'm going to factor it out. That factors as x plus 2 times x minus 2. That's the classic difference of squares. And that all goes over the original denominator of x minus 2. Now, what good does that do you? Well, actually a lot of good, because this factor of x minus 2 in the numerator cancels out with this factor of x minus 2 in the denominator. Anything divided by itself is one whole. So since those cancel out, we're left with the limit as x approaches 2 of just x plus 2. Now, we can reevaluate and substitute in this 2. So if I replace that in the x here, we have 2 plus 2, which is just 4. So the limit is 4, okay? So once you simplify the problem a little bit, you don't run into the division by 0 or 0 over 0, and you can actually ascertain the limit. So the limit is 4. Let's take a look at the graph right quick and see what that looks like visually. So this one here is linear or a straight line, and you can see as x approaches 2 here, if I put the mouse right onto it, says undefined, and that's true. The function value is undefined because of division by 0, but the limit is different. The limit is just approaching from both sides this x value of 2, and you can clearly see that we're approaching a height of 4 from either side. So if we could plug that hole, plug that little hole at 2 and plug it in, then we would have a function value of 4, which is the limit of 4, because that's the height that you're approaching, notwithstanding this little ridiculous little hole at 2. So this shows you again how you're approaching a height of 4, which is your limit. And moving on to our final example, we have the limit as x approaches -2 of a trinomial x squared plus 6x plus 8 all over x plus 2. So again, if we substitute in this -2, we would have -2 squared plus 6 times -2 plus 8 all over -2 plus 2. Well, what does that give us? -2 squared is 4. 6 times -2 is -12. 4 and -12 is -8 plus 8. There's that doggone 0. And the denominator, -2 plus 2, is also 0. So there's our 0 over 0. Well, what can we attempt to do? We can attempt to factor and see what happens. All right, so by factoring this out, let's see what we got cooking here. This is a trinomial, so that means that I need two numbers that multiply to give us +8 and add to give us +6 in the middle. So I'm thinking 4 and 2. So I have the limit as x approaches -2 of x plus 2 times x plus 4. Let me check it. X times x is x squared. Yep. The inside, the outside of the FOIL, 4 times x. And the inside, 2 times x, 4x and 2x is my 6x. Yep. And last, 2 times 4 is 8. Okay, that works. That's factoring a trinomial all over the denominator of x plus 2. Now, this is where the magic happens. We have a common factor in the numerator and denominator. These x plus 2's cancel out, which is exactly what I was hoping for. So now we have the limit as x approaches -2 of just what's remaining, which is x plus 4. Now, if we substitute in this limit value that we want to approach, -2, we have, substituting in -2 for x, we have -2 plus 4, which is just 2. So +2 is your limit. It's the value you are approaching from both sides. It is not the function value. That's an important distinction. So let's look finally one last time at Desmos and see how, while the graph is undefined at x equals -2, as x approaches -2, you're at a height of 2. Let's take a look. All right, so taking a look at this graph here, we can see that as x approaches -2, we are reaching a function value of 2. Of course, exactly at -2, we're undefined because of division by 0, but you can see that we're approaching this height of 2 from both sides. Thus, that is why the limit is 2. Again, you're not considering that small hole right at 2. You're converging on a height of 2 from both sides. So I hope this kind of makes sense how we're looking at this algebraically and graphically. At this point, my friends, we have reached the end of my tutorial video. So what I'd like you to do now is I'd like you to y'all try E, F, and G, which are 3 examples of scenario 3 where you should get 0 over 0. Please show your work and go through all the steps exactly like I've modeled for you. And when you're done with that, I want you to do mixed review, 3 more examples, substitute in the limit value, and then see where it takes you. It's either going to be scenario 1, 2, or 3. So give this your best shot, and I look forward to you doing some good work, and I hope you know a little bit more about limits analytically and graphically than you may have known before. Thank you so much and have a wonderful day.